Spontaneous processes, characterized by phenomena such as the flow of heat from regions of high temperature to those of low temperature, occur without the necessity of external energy input. In contrast, non-spontaneous processes require a source of energy to initiate and sustain their progression. This fundamental distinction is pivotal for the effective design of thermal systems and various appliances. Irreversible processes inherently contribute to an increase in entropy, representing a trend towards greater disorder within a system. This evolution towards chaos occurs without external influence, which is readily observable in everyday situations, such as the gradual disarray of a room that has not been tidied. Heat engines operate by transforming thermal energy from high-temperature sources to lower-temperature sinks, ultimately converting this energy into mechanical work. However, the efficiency of these engines is fundamentally limited due to inherent energy losses during the conversion process. A thorough understanding of this energy transformation is essential for enhancing engine performance. The efficiency of a heat engine is quantified using the formula that divides the work output by the heat absorbed. Grasping this equation is crucial for evaluating and comparing the performance of various types of heat engines. Power, defined as the rate at which energy is transferred, is typically measured in watts. By understanding the power output of an engine, one can engage in more informed comparisons and assessments regarding energy efficiency. To accurately calculate work output, it is necessary to comprehend the relationship between the heat absorbed and the heat discarded by a system. This knowledge plays a significant role in analyzing the performance metrics of thermal systems. Calculating thermal efficiency requires dividing the useful work output by the total heat absorbed by the engine. For instance, in a particular example, this methodology resulted in an efficiency of 12%, reflecting the practical capabilities of heat engines. The heat energy that is expelled into the environment constitutes a critical aspect of engine functionality. In one case study, it was determined that 154 kilowatts of heat energy was released, underscoring the significance of heat management in engine design. The efficiency of gasoline engines can be examined by comparing the work output with the heat input. In an illustrative example, an efficiency of approximately 20% was demonstrated, highlighting the inefficiencies typical in traditional combustion engines. During the process of isothermal expansion, heat energy is introduced into the system, enabling the gas to perform positive work as it expands. This phenomenon underscores the critical role of energy input in the operational dynamics of heat engines. The efficiency of the Carnot engine is derived from the temperatures of its hot and cold reservoirs, calculated using specific equations. This theoretical efficiency serves as a fundamental metric for evaluating the performance potential of real-world engines. Heat engines function by absorbing thermal energy from a designated hot reservoir while simultaneously discharging some heat to a cooler reservoir, thereby generating work in the process. This basic operational principle is foundational to numerous practical applications in thermal engineering. The coefficient of performance, or COP, is employed to assess the efficiency of refrigeration systems and heat pumps, with calculations differing based on the specific functions of each device. For refrigerators, COP emphasizes the amount of heat removed from the cold reservoir. Conversely, the COP for heat pumps is determined by the quantity of heat delivered to a warmer space rather than the heat extracted from a cold reservoir. This distinction is integral for effectively selecting appropriate heating solutions based on operational needs. To establish a maximum theoretical COP, one can utilize the temperatures of the respective hot and cold reservoirs. This calculation provides a benchmark against which the actual performance of heating systems can be measured, aiding in the determination of system effectiveness. In the context of refrigerators, the coefficient of performance, COP, is calculated through the relationship between the heat absorbed and the work performed. This assessment is critical for understanding the efficiency of heat transfer mechanisms. In a heat pump scenario, energy is extracted from the cold reservoir and then transferred to the hot reservoir. The relationship between work input and heat energy output is essential for comprehending the overall efficiency of these systems. The Otto cycle serves as the idealized model of a gasoline engine, depicting key processes such as adiabatic compression, isochoric heat addition, and subsequent energy conversion within the engine's operation. An understanding of the relationship between efficiency and compression ratio in thermodynamics is vital for a comprehensive grasp of engine performance. The video presents mathematical derivations illustrating these interconnections. The significance of the working substance within engines is emphasized, demonstrating how its intrinsic properties influence efficiency and performance calculations. Examples, such as steam engines, are highlighted to provide clarity on these concepts. Entropy is introduced as a quantifiable measure of disorder in thermodynamic systems, with a video elucidating how alterations in volume and temperature impact the entropy of gases as opposed to liquids and solids. In order to melt ice, it is necessary to add heat, a process that typically results in a corresponding increase in entropy, denoted as a positive delta S. This phenomenon occurs under isothermal conditions, where the temperature remains constant during the melting process. When temperature variations occur, the change in entropy can be approximated using the equation delta S equals Q divided by T, with T expressed in Kelvin. This necessitates the computation of heat based on mass and temperature differentials. For accurate calculations pertaining to entropy change, calculus proves invaluable, specifically through the application of the integral of Q/T. This methodology yields precise results when evaluating temperature fluctuations during heating or cooling processes. A comprehensive understanding of adiabatic processes is fundamental to thermodynamics, wherein no heat exchange transpires. This principle significantly influences entropy calculations and finds application across various mechanical systems. The Carnot engine serves as a salient example, elucidating the relationship between the heat absorbed from a hot reservoir and the heat released to a cold reservoir. This case underscores the principles of energy conservation within the context of thermal systems. In cyclic processes, it can be observed that the change in entropy remains constant at zero, emphasizing the equilibrium of energy transformations in reversible systems. This constancy is crucial for understanding the efficiency of thermodynamic cycles. The first method for calculating entropy change involves employing the formula Q divided by T, where Q represents the heat absorbed and T signifies the average temperature. This approach lays a foundational understanding of thermal dynamics. The second method applies the equation mc multiplied by the natural logarithm of the ratio of T final to T initial to determine entropy change under varying temperatures. This technique proves particularly effective in scenarios involving non-constant temperature. Both methods yield results that are closely aligned, thereby demonstrating the reliability of diverse calculation approaches within thermodynamics. This consistency encourages students to engage with multiple methodologies in their studies.